Good afternoon, everyone. Can everyone hear me? How are you guys doing? Why 6 out of 10? I'm also doing well, thank you. Just an extremely busy day. Why 0 out of 10? Quite sleepy. So I assume you had a extremely hectic day. So just on the admin side, I've created a Discord server for us to use. So I'm pasting the link to join the server in the chat. I will make an announcement on ClickUp as well for you guys to join the server. So I'm just going to use the Discord server as another means of communication and also um, another way to get information quicker to you. Okay, cool. I can see people starting to join the server. So yesterday I created a server and I made an announcement and I realized that I haven't provided you guys with the link. So I'm just going to send this in as well. So you can see the message I've just posted. Then the second piece of admin. Will you announce anything on the server exclusively? No, everything that's on ClickUp will be on the server as well. So nothing exclusively on the server. It's just another means of communication. And also, if you have questions about the work, it's also another means of communication. Then also on the admin side, this morning I've received an alarming amount of emails from facilities management and HOD from students trying to get access to the rooftops of some of the buildings to do their moon observations. Unfortunately, you guys are not allowed, or anyone in fact is not allowed to have roof access because a couple of years ago, students and some staff members committed suicide from the humanities building. And from now on, it's decided that no one whatsoever is allowed to have roof access, unfortunately. So when you do your observations, do them from areas that are open space, such as parking lots on campus. Just be mindful of your surroundings and safety. I don't want you guys to be 2 o'clock, 3 o'clock in the morning in an open field. So just keep that in mind. Do you guys have any questions? Anything before we start with today's class that you perhaps want to know? What is the procedure when it rains? Okay, so if it only rains 1 or 2 days, then you just add an extra 1 or 2 days to your observation schedule. But if it rains for more than 2 days, then you need to restart your entire observations. So yes, you can skip the day that's here. So if it rains, you skip that day and you just add an extra day to the end of your observations. There's no recommended date to start, but if you like, I can help you determine with your schedule what is the best date for you. It's a pleasure. So, in yesterday's class, we ended with a slide of how seasons happens on Earth, and that is due to Earth's cant of 23.4 degrees. Is everybody happy with this explanation and understand why we have summer and winter and different seasons? Can everyone still hear me? Everybody still happy with the explanation? Everybody happy where we are now? Awesome. And besides the sun and the moon, what also causes cycles in the night sky? Stars, but besides the stars, what else? Yes, Earth as well, but besides Earth, there's one thing that we are missing. Yes, our planets, the planets in our solar system. So the planets in our solar system also makes circles in the sky. And I think I quickly want to show you a video about circles in the sky. I can't remember if I shown you this video in yesterday's lecture. If I shown you, just please tell me, then I'll continue with the lecture. So let me quickly show you this video.
Under a dark sky, you can see thousands of stars. If you watch for a few hours, you can see them rise and set as the Earth rotates once a day. And if you go outside the next night at the same time, you'll see that things look pretty much the same as they did the night before. The stars rise and set, Polaris hangs to the north, and so on. One day hardly makes any difference to the sky's appearance. But what if you wait for another night or a week? If you're that patient and observant, you can spot subtle changes in the sky. Let's say a couple of weeks have passed. Remember that star that was just over a tree in the east when the sun set? The one that made you first notice the stars are rising and setting? Go look at it again. If you happen to be out at the same time, you'd expect that star to be in the same place. But it's not. It's actually a bit higher above the tree. And if you look west, stars that were well off the horizon just after sunset last week are now lower. If you wait a month, this effect is even more pronounced. All new constellations will be visible in the sky after sunset. This is because the Earth is going around the sun, literally changing our viewpoint on the sky. The Earth takes a year to orbit the sun once. Every day it moves a little bit along.
I'm going to stop sharing this. You say already seen this. Thank you for helping me with that. Then I'm going to show you rather, which one was it? I'm rather going to show you this one, because that continues on with this theme. There's two videos I want to show you. So the first one is this one.
Besides the sun, the moon is the most obvious object in the sky. Bright, silvery, with tantalizing features on its face, it's been the target of imagination, poetry, science, and even the occasional rocket. If you pay even the most cursory attention to it, you'll see that it changes every day. Sometimes it's up in the day, sometimes at night, and its shape is always changing. What causes this behavior? The moon is basically a giant ball of rock 3,500 kilometers across, hanging in space. Its surface is actually pretty dark, with about the same reflectivity as a chalkboard or asphalt. However, it looks bright to us because it's sitting in full sunlight. The sun illuminates it, and it reflects that light down to us here on Earth. And because it's a sphere and orbiting the Earth, the way we see it lit by the sun changes with time. That's what causes its phases. Geometry. The important thing to remember through all of this is because the moon is a ball and in space, half of it is always illuminated by the sun. This is true for the Earth too, and every spherical object in space. Half faces the sun, half faces away. We call the part facing the sun the daylight or bright side, and the half facing away the night or dark side. The phase of the moon refers to what shape the moon appears to us, how much of it we see illuminated from the Earth. The key to all this is this line dividing the lit day side from the unlit night side. We call that line the terminator. If you're facing the moon with the sun behind you, you're seeing the half of the moon that is fully illuminated by sunlight, and it looks full. If you're off to the side, you see half of the lit side and half of the dark side, and we say the moon is half. If the sun is on the other side of the moon, you're looking at the unlit half, and it looks dark. Now, mind you, I haven't moved anything except our point of view here. So at all times, the moon is always half lit and half dark. Remember that. The phase of the moon we see depends on from what direction the sunlight's hitting it, and the angle we see that from Earth. The moon orbits the Earth roughly once per month. In fact, that's where the word month comes from. Month and moon are cognates, words that have similar etymological histories. And in most languages, including English, the two words are very similar. The length of time we call the month is derived from the length of time it takes the moon to go through all of its phases, 29.5 days. So, to describe the phases, let's start at the beginning. New moon. New moon happens when the sun, moon, and Earth are all more or less in a line. The moon's orbit is actually tipped a bit to the Earth's, so sometimes the new moon happens when the moon is below the sun or above it. But at some point in its orbit, at some point in the month, it appears to be as close to the sun as it can. What does it look like from the Earth? The moon is between the Earth and the sun. So from our perspective, we only see the dark half, the unilluminated half of the moon. The other side, the far side of the moon, is lit, but we can't see it. It makes sense then to call this the beginning of the moon's cycle, hence the term new moon. Now think about this for a sec. Because the moon is near the sun in the sky, it travels across the sky with the sun. It's up during the day. You can only see it from the part of the Earth that's lit, which is when it's daytime. It's a very common misconception that the moon is only up at night, but it's up during the day literally just as often. At new moon, the moon stays near the sun, so it rises at sunrise and sets at sunset. This makes it extremely difficult to see. It is, after all, sitting next to the brightest object in the sky, and only a little bit of it is lit from our perspective. But not for long. Because the moon is orbiting the Earth, after a couple of days, it's moved a bit to the east. Now we're seeing it along a slight angle, and we can see a little bit of the illuminated half of the moon on its side toward the sun. The terminator, the day-night line, appears curved around the moon, so what we see is a thin, illuminated crescent moon. At this point, the crescent is still very thin, with the horns of the crescent pointing away from the sun. Note that the moon is still pretty close to the sun in the sky, just a bit to the east, rising maybe an hour or two after sunrise. But this means it's up all day and then sets after the sun does. This is the best time to see the crescent moon, when the sun is already set and the sky starts to get dark. The moon will be low over the western horizon, and it'll set soon after the sun does. Let's wait a couple of days. Okay, now the moon has moved a bit more in its orbit around the Earth and is farther from the sun in the sky. We see a little more of the illuminated part, and the crescent is wider. Since it's getting thicker, we say this is a waxing crescent moon. Waxing means growing or getting bigger. It's also well away from the sun now, so it's easier to spot even during the day before sunset. 7 or so days after new moon, we get to our first milestone. The moon is now 1/4 of the way around its orbit. It's 90 degrees away from the sun in the sky, which means we're looking straight down on the terminator, the moon's day-night line. It cuts right down the middle of the visible face of the moon, so it's half lit, with the sunward side of the moon visible and the other side dark. Confusingly, this phase is properly named first quarter because the moon is 1/4 of the way through its cycle, 1/4 of the way through its orbit around the Earth, even though it looks half full. So it's not really the half full moon. Astronomers prefer first quarter. So if you want to sound all astronomery, then you should call it that. But time marches on. The moon continues on its gravitational dance with Earth, swinging around its orbit. Now more than half full, we say its shape is gibbous, which means swollen or convex. Since it's getting wider, this is actually the waxing gibbous phase of the moon. It rises in the late afternoon and is up most of the night. Our next big step comes 2 weeks after new moon, when it's moved halfway through its orbit. It's now opposite the sun in the sky, 180 degrees around. The Earth is between the moon and sun, so we're looking at the fully illuminated half of the moon. This is the full moon. Because it's opposite the sun, it rises at sunset and sets at sunrise. It's up all night shining down on Earth. But again, wait a couple of days and things change. When the moon is full, it's 180 degrees around the sky from the sun. So as it continues to move around the Earth in a circle, the distance between it and the sun is now starting to decrease, even as it continues on in the same direction. As before, it keeps rising and setting later, but now it rises after sunset and sets after sunrise. If you get up early in the morning as the sun is just rising in the east, you'll see the nearly but not quite full moon setting in the west. Not only that, but we're about to go through all the phases again, but in reverse order. A few days after full moon, the lit side is shrinking. It's in the waning or shrinking gibbous phase. Then, 3 weeks or so after new moon and a week after full, the moon is once again half lit, the terminator splitting the moon's face in 2 even halves. This is the third quarter moon because the moon is 3/4 of the way through its cycle. It's a lot like first quarter, but the side that was lit is now dark and vice versa. It's 270 degrees around the sky from the sun. It rises at midnight and sets at noon. A few days later, and the moon is a crescent again, getting thinner. It's now a waning crescent. It rises just a couple of hours before sunrise and sets a couple of hours before sunset. Then finally, we're back where we started. 1 month after new moon, the moon has traveled 360 degrees around the sky and once again as close to the sun as it can get. It's new moon and the cycle starts up again as it has for time immemorial. An interesting thing happens if you move your perspective from the Earth to the moon. The phases of the moon we see from Earth depend on the angle of the moon and the sun in the sky. Moon, the angles are exactly 180 degrees reversed. At new moon, when the moon is between the Earth and sun, the Earth is opposite the sun as seen from the moon. It's full Earth. All the other phases are opposite too. So when we see a full moon, a moon dweller would see a new Earth, and so on. Have you ever looked at the thin crescent moon and seen the ghostly face of the rest of the unlit side? That's because it's not really unlit. The nearly full Earth is reflecting sunlight on the moon, lighting up the otherwise dark part. The Earth is bigger and more reflective than the moon, so it's actually 50 times brighter than a full moon. This glow is called Earthshine, a term I quite like. Even more poetically, it's been called the old moon in the new moon's arms, referring to the unlit part surrounded by the crescent new moon's horns. That's lovely, isn't it? The moon is one of the most beautiful and most gratifying objects in the sky to observe. It's different every day, yet it's also the same because we see more or less the same half of it, the same face all the time. It's big and bright, and the features on its surface discernible by eye, and even better with binoculars or a small telescope. As the phases change, inexorably, day after day, the angle of sunlight hitting the surface changes, bringing new things into our view. The motions become comforting, even familiar. It's a reminder that the universe may seem strange and complicated and forbidding at first, but over time, as you get outside and experience it, it becomes your neighborhood. Welcome home. Today you learned why the moon has phases. It's a sphere and it orbits. The solar system is the name we give to our local cosmic backyard. A better way to think of it is all the stuff held sway by the sun's gravity. The sun itself, planets, moons, asteroids, comets, dust, and very thin gas. If you took a step back, well, a few trillion steps back, and looked at it from the outside, you might define the solar system as the sun. And that's because the sun comprises more than 98% of the mass of the entire solar system. The next most massive object, Jupiter, is only 1/10 the diameter and less than 1% the mass of the sun. But that's a little unfair. Our solar system is a pretty amazing place, and you can figure out a lot of what's going on in it just by looking at it. For thousands of years, we had to explore the solar system stuck on this spinning, revolving ball, the Earth. The problem was, for a long time, we didn't know it was a spinning, revolving ball. Well, the ancient Greeks knew it was a ball. They had even measured its size to a fair degree of accuracy, but most thought it was motionless. When a few folks pointed out that this might not be the case, like the ancient Greek astronomer Aristarchus of Samos, they got ignored. The idea that the sky spins around the Earth seems obvious when you look up. And when great minds like those of the astronomer Ptolemy and the philosopher Aristotle supported that idea, well, people like Aristarchus got left behind. The basic thinking was that the moon, sun, and stars were affixed to crystal spheres that spun around the Earth at different rates. While it kind of sort of worked to predict the motions of objects in the sky, in detail it was really unwieldy and failed to accurately predict how the planet should move. Still, Ptolemy's idea of a geocentric universe stuck around for well over 1,000 years. It was the year 1543 when Nicholas Copernicus finally published his work proposing a sun-centered model, much like the one Aristarchus had dreamed up 2,000 years previously. Unfortunately, Copernicus's model was also pretty top-heavy and had a hard time predicting planetary motions. The last nail in geocentrism's coffin came a few years later, when astronomer Johannes Kepler made a brilliant mental leap. Based on observations by his mentor, Tycho Brahe, Kepler realized the planets moved around the sun in ellipses, not circles, as Copernicus had assumed. This fixed everything, including those aggravating planetary motion. It still took a while, but heliocentrism won the day. And the night, too. This paved the way for Newton to apply physics and his newly created math of calculus to determine how gravity worked, which in turn led to our modern understanding of how the solar system truly operates. The sun, being the most massive object in the solar system by far, has the strongest gravity, and it basically runs the solar system. In fact, the term solar comes from the word sol for sun. We named the whole shebang after the sun, so there you go. The planets are smaller, but still pretty huge compared to us tiny humans. At the big end, we have Jupiter, 11 times wider than the Earth and 1,000 times its volume. At the smaller end, we have, well, there is no actual smaller end. We just kind of draw a line and say planets are bigger than this. That's a bit unsatisfactory, I'll admit, but it does bring up an interesting point. I've been using the term planet, but I haven't defined it, and that's no accident. I don't think you can. A lot of people have tried, but definitions have always come up short. You might say something is a planet if it's big enough to be round, but a lot of moons are round, and so are some asteroids. Maybe a planet has to have moons. Nope. Mercury and Venus don't, and many asteroids do. Planets are big, right? Well, yeah, but Jupiter's moon Ganymede is bigger than Mercury. Should Mercury be stripped of its planetary status? I could go on, but no matter what definition you come up with, you find there are lots of exceptions. That's a pretty strong indication that trying to make a rigid definition is a mistake. It'll get you into more trouble than it'll help. Planet can't be defined. It's a concept, like continent. We don't have a definition for continent, and people don't seem to mind. Australia is a continent, but Greenland isn't. Okay by me. So that's what I tell people if they ask me if Pluto is a planet. I say, tell me what a planet is first, and then we can discuss Pluto. Pluto is what it is, a fascinating and intriguing world. One of thousands, perhaps millions more orbiting the sun out past Neptune. I think that makes it cool enough. All the orbits of the planets lie in a relatively flat disk. That is, they aren't buzzing around the sun in all directions like bees around a hive. The orbit of Mercury, for example, lies in pretty much the same plane as that of Jupiter. That's actually pretty interesting. Whenever you see a trend in a bunch of objects, nature is trying to tell you something. In fact, there are other trends that are pretty obvious when you take a step back and look at the whole solar system. For example, the inner planets, Mercury, Venus, Earth, and Mars, are all relatively small and rocky. The next four, Jupiter, Saturn, Uranus, and Neptune, are much larger and have tremendously thick atmospheres. In between Mars and Jupiter is the asteroid belt, comprised of billions of rocks. There are lots more asteroids scattered around the solar system, but most are in the main belt. Then, out beyond the orbit of Neptune is a collection of rocky ice balls called Kuiper Belt objects. The biggest are over 1,000 miles across, but most are far smaller. They tend to follow the plane of the planets too. But if you go even farther, tens of billions of kilometers from the sun, that disk of Kuiper Belt objects merges into a vast spherical cloud of these ice balls called the Oort cloud. They don't follow the plane of the inner solar system, but orbit every which way. So what do all these facts tell us about the solar system? We think they're showing us hints of how the solar system formed. 4.6 billion years or so ago, a cloud floated in space. It was in balance. Its gravity trying to collapse it was counteracted by the meager internal heat that buoyed it up. But then something happened. Perhaps the shockwave from a nearby exploding star slammed into it, or maybe another cloud lumbered by and rammed it. Either way, the cloud got compressed, upsetting the balance, and gravity took over. It started to collapse. As it did, angular momentum became important. That's a lot like regular momentum when an object in motion tends to stay in motion. But in this case, it's a momentum of spin, which depends on the object's size and how rapidly it's rotating. Decrease the size and the rotation rate goes up. The usual analogy is an ice skater starting a spin, then drawing their arms in. Their spin is amplified hugely. The same thing happened in the cloud. Any small amount of spin it had got ramped up as it collapsed. It flattened into a disk, much like spinning raw pizza dough in the air will flatten it out. As it collapsed, material fell to the center, getting very dense and hot. Farther out in the disk, where it was cooler, material started to clump together as little grains of dust and other matter randomly bumped into other little bits. As these clumps grew, their gravity increased and eventually started drawing more material in. These little blobs are called planetesimals, wee baby planets. As they grew, so did the center of the disk. The object forming there was a protostar, or, spoiler alert, the proto-sun. Eventually, its center got so hot that hydrogen fused into helium, which makes a lot of energy. A lot of energy. A star was born. The new sun blasted out fierce light and heat that, over millions of years, blew away the leftover disk material that hadn't yet been assimilated into planets. The solar system was born. Closer to the sun, it was warmer. Hydrogen and helium are very light gases, and the warm baby planets there couldn't hold on to them. Farther out, material in the disk, and the planets were bigger. Since it was cooler too, they could hold on to those lighter gases, and their atmospheres grew tremendously. Eventually, in their cores, they became gas giants. There was also a lot of water out there far from the sun in the form of ice. Smaller icy objects formed past Neptune, but space was too big and random encounters too rare. They didn't get very big, maybe a few hundred kilometers across. Millions, perhaps trillions of them got too close to the big planets and were flung hither and yon. Closer in, material between Mars and Jupiter couldn't get its act together to form a planet either. Jupiter's gravity kept agitating it, and impacts between two bodies tended to break them up, not aggregate them together. And there you have it, our solar system, formed from a disk sculpted by gravity. Echoes of that disk live on today, seen in the flatness of the solar system. This isn't guesswork. The math and physics bear this out. And not only that, we see it happening now, today. When we look at gas clouds in space, we see stars forming. We see protoplanetary disks around them. We see the planets themselves getting their start. We may think of ourselves as the solar system, but we're really just a solar system. The scenario that happened here so long ago plays itself out daily in the galaxy. We're one of billions of such systems. And remember, every atom in your body and everything you see around you, every tree, every cloud, every human, every computer, everything on Earth, even the Earth itself, was once part of that dense cloud. We are quite literally star stuff. Today you learn that the solar system is one star, many.
So that hopefully provides us with an overview of what is coming up next. You guys have any questions? Okay, so the planets of our solar system provide no visible light of their own. They are visible only by reflecting light. Mercury, Venus, Mars, Jupiter, and Saturn are all easily visible to the unaided eye and look like stars, but Uranus is usually too faint to be seen, and Neptune is never bright enough. If you were looking down on the solar system from the North Celestial Pole, you would see the planets moving in the same counterclockwise direction around their orbits, with the planets furthest from the Sun moving the slowest. Seen from Earth, the outer planets move slowly eastward along the ecliptic. In fact, the word planet comes from the Greek word meaning wanderer. Mars moves completely around the ecliptic in slightly more than 2 years, but Saturn, being further from the Sun, takes nearly 30 years. Mercury and Venus also stay near the ecliptic, but they move different from any other planets. They have orbits inside Earth's orbit, and that means they are never seen far from the sun in the sky. So, question, what is the likeliness of a new planet to form? So, in our early system, no new planets will form, because when a star is being born, or let me rephrase this, when a star is being formed, its planets that orbits around it develops at the exact same time when that star is being formed. So that is the same process that we're going to discuss in a later chapter. So no, in our solar system, no new stars will be formed. But in places where new stars are being formed, yes, there will be new planets being formed. Pleasure. By tradition, any planet visible in the evening sky is called an evening star, even though planets are not stars. Similarly, any planet visible in the sky shortly before sunrise is called a morning star. Perhaps the most beautiful is Venus, which can become as bright as magnitude minus 4.7. So now currently, when you just look east, to the west, when the sun is setting, you'll see a bright star in the west. That's not actually a star, that's Venus, that you can currently see when the sun is setting. So the cycles of the sky are so impressive that it's not surprising that people have strong feelings about them. Ancient people saw the motion of the sun around the ecliptic as a powerful influence on their daily lives, and the motion of planets along the ecliptic seemed similarly meaningful. The ancient superstition of astrology is based on cycles of the sun and planets around the sky. You have probably heard of the zodiac, a band around the sky extending about 9 degrees above and below the ecliptic. The signs of the zodiac take the names from the 12 principal constellations along the ecliptic. A horoscope is just a diagram showing the location of the sun, moon, and planets around the ecliptic, and a position above or below the horizon for a given date and time. So the ecliptic is the path the sun takes to the sky. So I'll show you the ecliptic again. So this is the ecliptic. So when we look at this is the sun, this is the earth. If we are on earth and we're looking towards the sun, so let's say we are, let me get something out to draw, just a different color. So let's say we are in this location right here, and we're looking towards the sun, then we'll see the sun appears as if it is in Virgo. A couple of months later, when we are here and we look towards the sun, it seems like the sun is now in Capricorn. And then this path the sun makes around, that is the ecliptic. Does that answer your question? Yes, the apparent motion of the sun, because it's not actually the physical motion of the sun, it is just how we perceive the sun. So remember, this is Earth orbiting around the sun. So say for example, Earth's location is here, we are looking towards the sun, then it appears the sun is in Pisces. If we continue on, let's say we are now here and we look towards the sun, then it appears that the sun is now in Gemini. So it's not actually the physical path the sun takes, but the apparent path it makes when we observe it throughout the year. Does that help? Awesome. So centuries ago, astrology was an important part of astronomy, but the two are now almost exact opposites. Astronomy is a science that depends on evidence, and astrology is a superstition that survives in spite of evidence. The signs of the zodiac are no longer important in astronomy, and that's one thing I pest is people that says, oh, I'm this zodiac signs and my personality is that. That's total rubbish. And then we also have astronomical influences on Earth's climate. So the seasons are produced by the annual motion of Earth around the sun. But subtle changes in the motion can have dramatic effects on climate. You don't notice these changes during your lifetime, but over thousands of years, they can bury continents under glaciers. Earth is warmer and there are no ice ages even at the poles. Scientists have found evidence of at least 4 ice ages in Earth's past. One occurred 2.5 billion years ago, but other 3 that have been identified have all occurred in the last billion years. Can any one of you identify which movie this image is from? No, we are not currently in an ice age. If we are in an ice age, literally the entire planet will be frozen over. So this image is from the world, the movie The Day After Tomorrow. Also a brilliant sci-fi movie to watch. Watch it, it's a very cool movie. So now we're going to talk about some of the climate cycles. Interstellar is a brilliant movie. Sometimes a theory or hypothesis is proposed long before scientists can find the critical evidence to test it. That happened in 1920 when engineer and meteorologist Milutin Milankovitch proposed what became known as the Milankovitch hypothesis, and that is that small changes in Earth's orbit, precession, and inclination affects Earth's climate and can cause ice ages. By the middle 1970s, Earth scientists were able to collect the data the Milankovitch had lacked. Oceanographers drilled deep in the ocean seafloor to collect long cores of sediment. In the laboratory, geologists could take samples from different depths in the cores and determine the age of the samples and the temperature of the oceans when they were deposited on the seafloor. From this, scientists constructed a history of ocean temperatures that convincingly matched the predictions of the Milankovitch hypothesis. The evidence seemed very strong, and by the 1980s, the Milankovitch hypothesis was widely considered the leading hypothesis to explain climate cycles during the current ice age. But science followed a mostly unstated set of rules that holds that hypothesis must be tested over and over against all evidence. In 1988, scientists discovered apparently contradictory evidence. So here we can see in figure A, as calculations based on a Milankovitch effect can predict temperature over time, and the warming illustrated by the globe shown here took place from 25,000 to 10,000 years ago and ended the last glaciation. Then image B. Over the last 400,000 years, changes in ocean temperature measured from fossils found in sediment layers from the seabed matched changes in solar heating predicted by the Milankovitch effect. So question, so climate is mainly based off precision? No. So what we realize is the way the Earth moves, its angle it's canted in, and remember it has precision, and in Earth's orbit changes a little bit day by day, so a little bit closer to Earth, a little bit further from Earth, but have a small wobble. That has influences on the climate. But currently, all data and all evidence shows that global warming has a much bigger effect than the natural effect that's happening. So now we get to the moon. Just as the planets revolve counterclockwise around the sun, as seen from the direction of the celestial North Pole, the moon revolves counterclockwise around Earth. The moon is about 0.5 degrees in angular diameter, and it moves eastward a bit more than 0.5 degrees per hour. In 24 hours, it moves 13 degrees. Thus, each night you see the moon about 13 degrees eastward of its location the night before. As the moon orbits around Earth, its shape changes from night to night in a month-long cycle. So just something to think about. We know when we're looking from the North Pole down to Earth, the moon is orbiting counterclockwise around Earth. If we zoom out further, we'll see that Earth and the other planets is orbiting counterclockwise around the sun. Who of you did ice skating before? So which direction do you go around the ice skating ring? Anti-clockwise, yes. Who of you has watched NASCAR before? So NASCAR, they also drive counterclockwise around a track. In athletics, which way do they run around the track? Also counterclockwise. So why is everything counterclockwise? So yes, coincidence. So the Earth, the Moon, the planets, and the Sun, you can all explain with science, because when everything formed, we will discuss that in a later chapter. It had a angular momentum, an angular rotation that is counterclockwise. That's why in our solar system, everything is orbiting counterclockwise around the Sun. But why is that athletics courses and stadiums and NASCAR and ice skating rings is counterclockwise? That's just coincidence. But it gives you something to think about. So the moon always keeps the same side facing Earth. So in some galaxies, do the planets revolve in a clockwise direction? Yes, not in even galaxy, in our own galaxy as well. So remember, our galaxy consists out of hundreds of thousands of star systems. So in some star systems, everything is in a clockwise rotation. It all depends on what happened when that star formed, and we will discuss that in a later chapter. So the moon always keeps the same side facing Earth. The man is the moon is produced by the familiar features of the moon's near side, but you never see the far side of the moon. The changing shape of the moon as it passes through its cycle of phases is produced by sunlight illuminating different parts of the side of the moon that you can see. And notice a difference between the orbital period of the moon around Earth, so the sidereal period, and the length of the lunar cycle called the synodic period. So the question is, why don't we see the other side of the moon? Or the far side of the moon? Or referring to Pink Floyd's album, The Dark Side of the Moon. Yes, Mr. Wiley.
Sir, isn't it because the moon rotates at the same speed it revolves?
Yes, that's exactly it. So what happens if the speed at what the moon rotates around its own axis is also the exact same speed that it moves in its orbit around Earth? So that means the moon is tidally locked to Earth. Yes, Mr. Steyn, you are correct. We are tidally locked to Earth. So that's why we only see one side of the moon. Does everyone understand that? Awesome. So in this image, we can see the full lunar cycle. So the sequence shows the lunar phases night after night through a month, from the first crescent at upper left to the last crescent at lower right. To the last crescent at upper left. Notice that you see some face of the moon each night. The same mountains and craters and plains. It is changing directions of sunlight that produces lunar phases. And in your moon assignment, you will see 10 of these different phases, depending on where you start your observations. So how are these phases created? So let's say we are in a spaceship and we are above the Earth. So here is the North Pole, and we are in a spaceship a couple of 100 kilometers above the North Pole, and we are looking down on Earth. So when the moon is in between Earth and the sun, that means the far side of the moon is illuminated, and the side that points towards Earth, are we seeing the moon shadow, and that is new moon. Continue on, we have the waxing crescent. Continue on, first quarter, until we have the other side. So here, the moon is pointing away from the sun. So here, the face pointing towards us is illuminated, and its shadow is on its backside. And so it continues on through the entire cycle. Does everyone understand this? Are there specific dates for these phases? Yes. So if you go through on your assignment, one thing that you'll notice is a full moon will always occur on a specific date. A new moon will always occur on a specific date. That's something, one of the patterns you'll realize. Waxing gibbons and waxing crescent. So waxing gibbons and waxing crescent, let's see. What is the best I can show you? So see this right here. So here's a new moon that you don't see the Earth at all. So when you go back to this would be a waxing crescent, and that would be a waxing gibbons. Does that make sense? That's basically the intermediate phases between third quarter and first quarter. Have any one of you observed a lunar eclipse before? So lunar eclipses aren't rare events. There happens quite a few lunar eclipses during the year. Usually in a bad year, you would see at minimum 2 lunar eclipses. In a good year, you can see a few of them. But what happens in a lunar eclipse? In a lunar eclipse, the moon passes through Earth's shadow. So that is actually quite spectacular to see. And if you Google when will the next lunar eclipse in South Africa be, let's actually Google it to see when the next one will be. So the next lunar eclipse will be the 18th of September this year, which is very cool to see. And then next year, on the 14th March, will be a full lunar eclipse. So that's not a rare event, and that's something you can see quite regularly. So the lunar eclipse can occur at full moon if the moon moves through the shadow of Earth. Because the moon shines only by reflected light, the moon grows dark while it is crossing the crossing through the shadow. The umbra is the region of total shadow. If you were drifting in your spacesuit in the umbra of Earth's shadow, the sun would be completely hidden behind Earth, and you would see no portion of the sun's bright disk. If you drifted into the penumbra, however, you would see part of the sun peeking around the edge of Earth. So you would be in partial shadow if the penumbra sunlight is dimmed but not extinguished. So what that means is, if we have, so let's say this is the sun, and this is the Earth, and here is the moon going through. So when we are in this part, this dark region, that's the umbra, means we are totally covered by Earth's shadow. But when we are here, pieces of light still continues where something to write with, peaks around Earth. So when we are in this region right here, we get partial light, and that is the penumbra. Does everyone understand this concept? And this is something I might ask in a test in the exam. What is the umbra? What is a penumbra? So putting this in perspective, here we can see the umbra where the moon is moving forward, and this is the penumbra. Everybody happy with this explanation? Okay, so putting this, briefly explain it again. So you can, let's use different colors this time. So let's use green. So when we are in this region here, this is the total shadow of Earth. So when anything moves through this area, no sunlight will fall onto it. And that's why we have a total lunar eclipse in this area, because we are in the shadow of Earth. But if we are in this area over here, then we can see light from the sun can shine around Earth. So that meaning there's not that maximum amount of light, but a little bit of light in this area over here. And that is called the penumbra. You guys happy with this? Awesome. So this is how a lunar eclipse will look like. So you will have your full moon, then a partial face of being covered, and a little bit more and a little bit more. So we're not imagining we're on the moon. This is actually what we are seeing from Earth. And then, how many of you have seen a solar eclipse? So solar eclipse is also not a rare event. A solar eclipse happens in a bad year once a year, usually 2 times a year across Earth. But it depends on where we are in our rotation around our own axis, we can see. So there's now a full solar eclipse coming up in the United States and the Northern Americas. I think next year there's another one in South Africa. So it's also not a rare event, but it's depending on where you are on Earth. But it happens. So actually, let's see, when is the next solar eclipse in SA? So the next full eclipse we can basically see is the 6th of February 2027, and we can see a partial solar eclipse on 17 February 2026. So yes, that happens. But also it's not a rare event. So from Earth, you can see a phenomenon that is not visible from most planets. It happens because the sun is about 400 times larger than our moon, but also on average nearly 400 times further away. So the sun and the moon have nearly equal angular diameters of about 0.5 degrees. This means that the moon is just the right size to cover the bright disk of the sun and cause a solar eclipse. If the moon covers the entire disk of the sun, you see a total eclipse. If it covers only part of the sun, then you see a partial eclipse. So let's go through this example. So with this example is one way you can calculate the diameter of the moon for your assignment. So this is about one of 5 methods you can use. So figure 3.7 shows the relationship between the linear diameter and angular diameter. Is there a name for the area the moon shadow covers? So the moon shadow on Earth. As far as I understand, there's not a specific name for it, but just a shadow of the moon. So figure 3.7 shows the relationship between the linear diameter, angular diameter, and distance of an object. In this case, the moon. So the linear diameter is simply the distance between an object's opposite sides. You're referring to the linear diameter when you order a 16-inch pizza. The pizza is 16 inches across. The average linear diameter of the moon is 3,470 kilometers. The angular diameter of the moon is the angle formed by lines extending towards you from opposite sides of the object, meeting at your eye. Clearly, the further away a given object is, the smaller its angle diameter. To find the angular diameter of the moon, you need to use a small angle formula. It allows you to calculate the angle diameter of any object, whether it's a pizza or the moon. This formula is very important in astronomy, and you will encounter its uses many times in later chapters. So the equation is, we have the angular diameter divided by 2.06 times 10 to the power 5, and that equals the linear diameter of a distance. So now we just plug in our different variables. So in the small angle formula, you must always use the same units for distance and linear diameter. The version of the formula shown here has arc seconds as the unit of angular diameter. You can use this formula to find any one of the 3 quantities involved: linear diameter, angular diameter, and distance, if you know the other 2 by cross multiplying. So in this example, the moon's linear diameter is 3,470 kilometers, and its average distance from Earth is 384,000 kilometers. What is its angular diameter? So what we do is we plug all our values in, and we literally solve for the angular diameter, and that is 31 arc minutes, and that translates to about 0.5 degrees. So it's basically a straightforward plug and play scenario. So with a solar eclipse, the moon is between Earth and the sun, and because the moon and the sun are such a ratio that the sun is 400 times bigger than the moon, but also 400 times further away, it covers up. So then it casts a shadow on Earth. So when we are in this dark part over here, it is when we are in the umbra of the eclipse, and we will have a total solar eclipse. But if you are in this region over here, you are in a penumbra, and you will have a partial solar eclipse. Is that one of the formulas we need to know? Yes, that's one of the formulas, and I remember I will also give you a formula sheet when you need to use equations. So when we look here, so here we are in the umbra, and the umbra is the full eclipse, and the penumbra is a partial eclipse, and this is how a solar eclipse works. You guys happy with this explanation? Awesome. So this is how a full eclipse will look like when you observe it. You'll start seeing the moon moving in front of the sun, so a little bit, little bit, little bit, little bit, and then a full eclipse, and then it will start moving away. So umbra and penumbra can be applied to both lunar and solar eclipses. Yes, that is correct. So, do you guys know Bill Nye, the science guy? So, one of his interesting quotes is everyone you will ever meet knows something you don't. So, this was our lecture slides on chapter 2 and chapter 3. Do you guys have any questions? So if we are in umbra, will we be in complete darkness although it's daytime? No. So with a lunar eclipse, when we are in the umbra, yes, we will be in complete darkness when we are in the umbra. If we are in a penumbra, we won't be in complete darkness. So blood moons is nothing really causes a blood moon. It's just a terminology used. So blood moon just describes when a certain moon will happen. So let me see if I can quickly see if I can remember what is the definition of a blood moon again. So a blood moon is basically a complete lunar eclipse. So in a complete lunar eclipse, when you're on a penumbra, and you can still see a bit of light on the moon, and also from Earth's surface, a bit of light is reflected, then the moon appears a little bit reddish. And that is why it's referred to as a blood moon, but a blood moon is basically a full lunar eclipse. So for how long does a total solar eclipse last approximately? So a lunar eclipse is, for the full eclipse time, only about 20 to 30 minutes. For a total solar eclipse, that's also not very long. That's also about 20 to 30 minutes. So how did life form from stars, rocks, cloud, and gravity? So that is something we are going to discuss in the last chapter of our textbook. So question, do you think that there is life beyond planet Earth? Yes, I definitely think so. So we will discuss that in the last chapter, but if we look at a statistic, there are about 200 billion stars in our Milky Way galaxy. From that 200 billion stars, half of those stars have planets in the Goldilocks zone, so meaning planets in the correct distance from the host star that is not too cold, not too warm, and just right. So there is possibility to have life. So who's to say in that stars that there's no planets that have life? So yes. If there isn't a waste of space, This last. I know our solar system itself is moving, but is it revolving around a black hole in the Milky Way? Yes, it is. So remember, something needs to keep all the material, all the stars in our galaxy together. So all galaxies has a supermassive black hole in its center. And everything else revolves around that supermassive black hole. So you can think about the supermassive black hole as our own sun. So our sun keeps our planets from orbiting it. The same principle goes to the black hole. But we will talk about that in another chapter as well. So for our next set of lecture slides, we are going to look at chapter 4 and chapter 5 in the textbook. So how are black holes formed? We will talk about how that is formed in later chapters as well. But a black hole is formed when a massive star reaches the end of its own life. So our own sun won't become a black hole because it doesn't contain enough mass. So when a star's at the end of its lifetime, usually one of three things happens. It either becomes a white dwarf or a neutron star or a black hole. So our own sun will just basically burn up all of its fuel that it has, and it will still radiate a little bit of energy. We call that a white dwarf. And once it's finished radiating all of its energy, it becomes a black dwarf, and it's just the dead core floating in space. When you have more solar mass, so we speak about solar mass as the mass of our own sun. So our own sun has a solar mass of 1. For a star that has between 4 and 10 solar masses, at the end of its life, it will blow out its outer layers of its surface and atmosphere, making it a nova. And then the core will collapse in on itself, but it will stop at a point and that will form a very dense object called a neutron star. But a neutron star, look in your questions, a neutron star cannot be turned into a black hole. So what happens is in a very large star, so a star with 10 plus solar masses, at the end of its lifetime, it will blow off its outer layers, called a supernova explosion, and then the core will collapse in on itself. But that causes a runaway effect that we will discuss in a later chapter, and that keeps squeezing everything into a smaller point, and that smaller point we call a singularity, and a singularity is a black hole. So how's the sun's gravity distributed through the solar system? It is distributed normally. So that's why we can use Newton's laws. So remember, we can use Newton's law of universal gravitation. That means one body will attract another body. So that means the closer you are to the object, the higher the gravitational pull is. The further you are away from the object, the less gravitational pull is. Same principle in orbit around Earth. If we are on Earth's surface, gravitational pull is high. But if we are International Space Station, 400 kilometers above ground, then you are weightless. So question, so for the previous chapter, do we need to define details like the angles, for example, or it's just a general idea? So what is the difference between voids and black holes? So voids are areas in space where you don't really see any stars, but it doesn't matter, there's not any material. So usually in voids, you can see in different wavelengths, there could be clouds of gases, but no stars. But with black holes, we don't know what's happening inside a black hole because not even light can escape it. So that seems to be that there's nothing inside. Does that answer your question? So then theoretically, can we squeeze a person so dense that they become a black hole? Yes, you can. Theoretically, you can. So in theory, if we would squeeze our own sun, become a black hole, then the black hole of our own sun will be the size about of a grape. But our own sun won't become a black hole because it doesn't have enough mass. So you want to go through the angular diameter calculation again. Okay, let me get that lecture slide out. So the angular diameter equation is straightforward, easy, plug and play. So here we'll see on this side of the equation, we have angular diameter over 2.06 times 10 to the power 5. We will learn later where this comes from, but you can also Google it. Then here we have linear diameter, and here we have distance. So in this example, we have the moon's linear diameter, that's 3,470 kilometers. So then we can literally take this number, plug it in here. We have the average distance from Earth to the moon, that's 384 kilometers. We plug in there. We have this value over here, so this value here is the only unknown. So then we just literally solve the equation to solve this. So to solve this, we literally multiply this over to that side of the equation, and we solve it, and we get 31 arc minutes. And 31 arc minutes equates to 0.5 degrees. Does that help? So for your assignment, you can use the small angle formula, but then you need to show calculations of how do you get this angle, because you need to add how do you get this angle, and how do you get this distance. So then it's up to you where you get this. So that's not a minus, that is an equal sign. So this is an equal sign. It is a pleasure. So let's go to our new set of lecture slides. To figure out the angle. So that is why it's a research project. So you can read up about it. If you get stuck, then you can ask me again. So for this new set of lecture slides, we're going to look at chapter 4 and chapter 5 in the textbook. So for this lecture, we are going to look at the origin of modern astronomy, classical astronomy, and Newtonian astronomy. So wouldn't the calculation already exist online? Yes, it would, but you need to explain everything. And that's why you need to make your own, so you can use the values online, but then I would know how you got those values. So you need to measure your own angle, for example. And there is ways to measure it. So the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff, and this was said by legendary Carl Sagan. Do you guys know who Carl Sagan was? So Carl Sagan is one of our modern astronomers, and he was a great astronomer. Go read up about him. He also started the Planetary Society. So he was one of the greatest minds of our time and recently. And he said this, and if you think about it, the elements named the nitrogen, calcium, iron, carbon, even gold, silver, platinum, They are not naturally occurring on Earth. Those elements are not even created in the fusion process of stars. The only place where these elements are formed are in supernova explosions. And so there were supernova explosions, it scattered these elements across space. And when Earth was formed, they were caught up in the process, and that's how we got them on Earth. And that's why they are also part of us. So that is just something to think about. So how did humanity first realize that we live on a planet moving through space? And that required the revolutionary overthrow of ancient and honored idea of Earth's place. By the 16th century, many astronomers were uncomfortable with the theory that Earth sat in the center of a spherical universe. Do you guys know who these three gentlemen are? Nicholas Copernicus, Galileo Galilei, and Sir Isaac Newton. So now we're going to talk about where they fit in the origin of astronomy. So in this chapter, we are going to investigate 4 questions. How did classical philosophers describe Earth's place in the universe? How did Copernicus revise that ancient concept? Why was Galileo condemned by the Inquisition? And how did Sir Isaac Newton change humanity's view of nature? So here is another quote of William Whewell. Astronomy is the only progressive science which the ancient world produced. How you would burst out laughing, my dear Kepler, if you would hear what the greatest philosopher of the gymnasium told the Grand Duke about me, from a letter by Galileo Galilei. As early civilization developed, great philosophers struggled to understand the movements of the sun, moon, and planets. Later mathematical astronomers made precise measurements and computed detailed models in their attempts to describe the celestial motions. It took hard work and years of effort, but the passion of astronomy gripped some of the greatest minds in history and drove them to try to understand the sky. The first theme we will investigate is the struggle to understand the place of Earth. It seemed obvious to the ancients that Earth was the center of debate over the place of Earth involved deep theological questions and eventually led Galileo before the Inquisition. The second time we will investigate is the long and difficult quest to understand planetary motion. Astronomers built more and more elaborate mathematical models, but I still could not predict precisely or explain the motion of the visible planets along the ecliptic. That mystery was finally solved when Isaac Newton described gravity and orbital motion in the late 1600s. The great philosophers of ancient Greece wrote about many different subjects, including what I saw in the sky. Those writings became the foundation on which later astronomers built modern astronomy. Do you guys know who this is? So this is Aristotle. So the Aristotelian universe. So the first thing we're going to discuss is a first principle. The first principle is something that is held to be obviously true. Once a principle is recognized as true, whatever can be logically derived from it must also be true. So you've probably done things from first principles in mathematics and in physics. So have you done limits from first principles? Or you're probably busy with it now? So that means that everything you derive further from that first principle must also be true. And that is where we come into astronomy. What is the first principles of astronomy? For 2,000 years, the minds of astronomers were shackled by a pair of ideas. The Greek philosopher Plato argued that the heavens were perfect because he considered the only perfect geometrical shape to be a sphere, and turning sphere carries a point on its surface around in a circle, and became the only perfect motion is uniform motion. Plato concluded that all motion in the heavens must be made up of combinations of circles turning at uniform rates. This idea was called uniform circular motion. Plato's student Aristotle argued that Earth was imperfect and lay at the center of the universe. Such a model is known as a geocentric universe. His model contained 55 spheres turning at different rates and at different angles to carry across the sky the 7 celestial objects called planets at a time: the Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn. Aristotle was known as the greatest philosopher in the ancient world, and for 2,000 years his authority limited the imaginations of astronomers to uniform circular motion and geocentrism. So this is the model of the Aristotelian universe. So Earth is in the center, Aristotelian universe, and everything revolved around Earth. So in one of the videos, we discussed this topic as well, and that is parallax. And you can do it where you are sitting right now. So if you look at something stretched out, for example, your left arm, your left thumb, and you cover an object that is far away, and you close your right eye and you look to your left eye, then you'll see your object is covered. But now, closing your left eye and looking for your right eye, you'll see that your thumb has moved a little bit. And that is due to the distance between your two eyes getting bioscopic vision. And that leads to parallax. So that little angle it makes is called parallax. So early astronomers believed that Earth did not move because they saw no parallax, the apparent motion of an object caused by the motion of the observer. So to demonstrate parallax, close one eye and observe a distant object with your thumb, held at arm's length. Switch eyes and your thumb seems to shift position as shown in the image. If Earth moves, they reasoned you should see the sky from different locations at different times of the year. And you should see parallax distorting the shapes of the constellations. They saw no parallax, so they concluded Earth does not move. Actually, the parallax of the stars is too small to see with the unaided eye. Every 2.14 years, Mars passes through a retrograde loop. 2 successive loops are shown in the next image. Each loop occurs further east along the ecliptic and has its own shape. Simple uniform circular motion centered on Earth could not explain the retrograde motion. So ancient astronomers combined uniformity rotating circles, much like gears in a machine, to try to reproduce the motions of the planets. So we will discuss retrograde motion in a moment. So what happens is when we are moving along the ecliptic, it seems like Mars is moving this way, then all of a sudden backwards, and all of a sudden this way again. And then later on, it seems that Mars is moving forward, backward, and then forward again. What's happening during these positions is because Earth is in an orbit closer to the Sun than Mars, then at these 2 points, Earth is moving past Mars, so that it seems like Mars is moving backward, and then when we are further away, it seems like it's moving forward again. So right here is where Mars and Earth moves in the same direction. Here, Earth overshoots Mars, and it seems like Mars then is going backward when it's actually not. It's just as we perceive it. And when we are far away, it seems like it is moving forward. You guys understand this concept of retrograde motion. So that is something the uniform circular motion could not explain. That couldn't explain retrograde motion, and thinking Earth is a center of the universe, that also couldn't explain that motion. So uniformly rotating circles were the key elements of ancient astronomy. Ptolemy created a mathematical model of the Aristotelian universe in which the planets allowed a small circle in the ecliptic that slid around the larger circle called the deferent. By adjusting the size and rate of rotation of the circles, he could approximate the retrograde motion of a planet and see the illustration on the right. To adjust the speed of the planet, Ptolemy supposed Earth was slightly off-center, and that the center of the ecliptic moved such that it appeared to move at a constant rate as seen from a point called the equant. To further adjust this model, Ptolemy added a small epicycles, not shown here, riding on the top of large epicycles, producing a highly complex model. Ptolemy's great book, Mathematica Syntaxis, published around the year 140, contained details of his model. Islamic astronomers preserved and studied the book through the Middle Ages. They called it Al-Majesty, so the greatest. When the book was translated from Arabic to Latin in the 12th century, it became known as the Almagest. Do we need to know terms like equant? No, you don't need to know these terms. This is just for background information. So the Ptolemaic model of the universe shown below was geocentric and based on uniform circular motion. Note that Mercury and Venus were treated differently from the rest of the planets. The centers of epicycles of Mercury and Venus had to remain on the Earth-Sun line as the Sun circled Earth through the years. All of this just background? Yes, so this right now is still background information. Equants and smaller epicycles are not shown here. Some variations of this model contain nearly 100 epicycles added by generations of astronomers trying to fine-tune the model to better reproduce the observed motions of the planets. Notice that this modern illustration shows rings around Saturn and sunlight illuminating the globes of the planets, features that would not have been known before the invention of the telescope. So with the Aristotelian universe, it says that everything is revolving around Earth. So Mercury, Venus, the Sun, but we know this is not correct. So the Copernican revolution. So you would not have expected Nicholas Copernicus to trigger a revolution in astronomy and science. He was born in 1473 to a merchant family in Poland. Orphaned at the age of 10, he was raised by his uncle, an important bishop, who sent him to the University of Krakow and then to the best universities in Italy, where he studied law and medicine. Nevertheless, he had a passion for astronomy even as a student. Sometime before 1514, he wrote an essay proposing a model of heliocentric universe in which the Sun, not Earth, was the center. In the Copernican system, Earth moves faster along its orbit than the planets lie further from the Sun. Consequently, Earth periodically overtakes and passes these planets. To visualize this, imagine that you are in a race car driving rapidly along the inside lane of a circular racetrack. And as you pass slower cars driving in the outer lanes, they fall behind. And if you did not realize you were moving, it would look like these cars in outer lanes occasionally slowed to a stop, then backed up for a short interval. And that is the explanation of retrograde motion. So here we can see it's moving this side. Here Earth's overtaken because its orbit is closer to the Sun, and then it's moving forward again. So Copernicus could explain retrograde motion without epicycles, and that was impressive. The Copernican system was elegant and simple compared with the whirling epicycles of the off-center equants of the Plotnik system. However, their revolution has failed in one critical way. The Copernican model could not predict the positions of the planets significantly more accurately than the Plotnik system could. Copernicus proposed a revolutionary idea when he made a planetary system heliocentric, but he was a classical astronomer with tremendous respect for the old concept of uniform circular motion. In fact, Copernicus objected strongly to Plotny's use of the equant because it required that a planet move faster in some places and slower in others. It seemed arbitrary to Copernicus, an obvious violation of uniform circular motion, and the elegance of Aristotle's philosophy of the heavens. Copernicus called equants monstrous because they undermined both geocentrism and uniform circular motion. In devising his model, Copernicus demonstrated a strong belief in uniform circular motion. Although he did not need epicycles to explain ring motion, this was the exact, let's go back. Retrograde motion, Copernicus quickly discovered that the sun, moon, and the planets suffered all other small variations in their motions that would not explain using uniform circular motion centered around the sun. Today, astronomers recognize that those variations are the result of planets following slightly non-circular elliptical orbits. But because Copernicus held firmly to uniform circular motion, he had to introduce small epicycles to try to reproduce these minor variations in the motions of the sun, moon, and planets. The Copernican model is inaccurate. It includes uniform circular motion and consequently does not precisely describe the motions of the planets. But a Copernican hypothesis that the universe is heliocentric is correct, considering how little astronomers of the time knew of other stars and galaxies. The universe that Copernicus knew was heliocentric in that the planets circle the sun and not Earth. The Copernican universe was elegant in its arrangement and its motions. Mercury and Venus are treated just like all other planets, and orbital velocities, so the blue arrows, decrease smoothly from that of Mercury, the fastest, to that of Saturn, the slowest. Compare the elegance of this model with the complexity of the Plotnik model as shown at the top right of the hand page of Concept Art 4A in the textbook. The Copernican hypothesis showed the problem of the place, but it didn't explain planetary motion. If planets didn't move in uniform circular motion, how did they move? The puzzle of planetary motion was solved during the century following the death of Copernicus through the work of two men. One compiled the observations and the other did the analysis. So the first person is Tycho Brahe. Although Tycho officially studied law at a university, his real passions were mathematics and astronomy. And early as university days, he began measuring the positions of the planets in the sky. In 1563, Jupiter and Saturn passed very near each other in the sky, nearly merging into a single point on the night of August 24. Tycho found that the Alphason tables were full month in error and that the Prutenic tables were in error by a number of days. So those tables predicted where the different planets would be in the night sky at certain times of the year. In 1572, a new star called Tycho's supernova appeared in the sky, shining more brightly than Venus, and Tycho carefully measured its position. According to classical astronomy, the new star represented the change in the heavens, and therefore had to lie below the sphere of the moon. So Tycho, even though he believed in a geocentric universe, understood that the new star should show parallax, meaning that it would appear slightly too far east as it rose, and slightly too far west as it set. But Tycho saw no parallax in the position of the new star, so he concluded it must lie above the sphere of the moon and was probably in the starry sphere itself. This contradicted Aristotle's conception of the starry sphere as perfect and unchanging. No one before Tycho could have made this discovery because no one had ever measured the positions of celestial objects so accurately. Tycho had great confidence in the precision of his measurements, and he had studied astronomy thoroughly, so when he failed to detect the parallax for a new star, he knew it was important evidence against the Ptolemaic theory. He announced his discovery in a small book, the Stella Nova, or the New Star, published in 1573. And then we had this guy. Do you know who this is? This is Johannes Kepler. Have you guys heard about Kepler's laws? So Kepler's laws is a question I usually like to ask in the tests and exams. So I might ask, what are Kepler's three laws? Explain Kepler's three laws, illustrate his three laws, yes, of planetary motion. So his first laws of planetary motion is, the first law is the orbits of planets are ellipses, with the sun at one focus. The second law is a line from a planet to the sun sweeps over equal areas and equal intervals of time. And the third law is a planet's orbital period squared is proportional to its average distance from the sun cubed. So this is a formula you should know. So what does this actually mean? Kepler's first law, each planet's orbit about a sun is the eclipse. The sun's center is always located at one focus of the orbital ellipse. The sun is at one focus. The planet follows the eclipse in its orbit. The planet to the sun distance is constantly changing as a planet goes around its orbit. So do all of these laws still hold true? Yes. And Kepler's laws is one of the key aspects of orbital mechanics, and we use those laws to put satellites in orbit. So when we visualize it, you can see this is an ellipse. An ellipse has two focus points. One is this side, one of that side. So the law states that the sun is always in one of these focus points. And all planets move about the sun in elliptical orbits, having the sun as one of the foci, so one of the focal points. And that's basically the sweet and short of Kepler's first law. The second law, the imaginary line joining a planet and the sun sweeps equal areas of space during equal time intervals as the planet orbits. Basically, that planets do not move with constant speed along their orbits. Rather, their speed varies so that the line joining the centers of the sun and a planet sweeps out equal parts of an area in equal times. The point of nearest approach of a planet to the sun is terminated at perihelion. So when they are the closest point, so remember, this is another definition I can ask you, the point of nearest approach of the planet and the sun, or the planet and another point, so planet and the sun, is perihelion. The furthest point is aphelion. So the point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is at perihelion and slowest at aphelion. So that means is when we look at this point here, here's the sun at one foci or focus point. So when we are at this point here, the sun moves faster. So when we are slower, so at aphelion, the sun moves slower. But the shaded area A1 and the area A2 is the exact same size. So it just means is here the sun moves faster and here the sun moves slower. But this area covered is 1 month, this area covered is 1 month. So a radius vector joining any planet to the sun sweeps out equal areas and equal lengths of time. Are you all happy with this definition and explanation? Okay, no repeat. So what this means is, let me get a drawing, something to draw out with. So that means this is the orbit of Earth around the sun or any other planet. So what that means is, let's take another color. This is a distance of 1 month, and this is also a distance of 1 month. But to cover that point, the Earth is closer to the Sun. So this place right here, Earth will move faster in its orbit. And here it will move slower in its orbit. But these shaded areas are exactly the same area size. So that basically means is here Earth moves faster, here Earth moves slower, but it still covers a time area of 1 month. And that is Kepler's second law. Does that help? Pleasure. Then Kepler's third law. The squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. So Kepler's third law implies that a period of the planet to move the Sun increases rapidly with the radius of the orbit. Thus, we find that Mercury, the innermost planet, takes only 88 days to orbit the Sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. But Kepler hadn't known about gravitation when he came up with the 3 laws. They were instrumental in Isaac Newton's deriving his theory of universal gravitation, which explains the unknown force behind Kepler's third law. Kepler and his theories were crucial in the better understanding of our solar system dynamics, and as the springboard to newer theories that more accurately approximate planetary orbits. So the only thing we need to know for this equation, or this is basically this formula right here. So we need to know basically this formula. This is Kepler's law. And we can also change it in this way when we substitute the value for k is equal to 1. And that is the sweet and short of what Kepler's laws are. So when we plot this and put it together, here we have orbital period in years on our y-axis, and the semi-major axis is distance from the Sun in AU. So here we can see Mercury orbits the fastest, then Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptunus, Pluto. And we're making use of the same principle. Here we can look at Jupiter's 4 biggest moons, Io, Europa, Ganymede, and Callisto. So Io is closer to Jupiter. Its orbit's the fastest, then Europa, then Ganymede, then Callisto. So the Rudolphine tables that we've mentioned are just tables that calculate where the positions of certain planets and objects would be. So the Rudolphine tables was Kepler's masterpiece. It could predict the positions of planets 10 to 100 times more accurately than previous tables. So Kepler's tables were the precise model of planetary motion that Copernicus had sought but failed to find. The accuracy of the Rudolphine tables was strong evidence that both Kepler's laws of planetary motion and the Copernican hypothesis for the place of the Earth was correct. Do you all know who Galileo Galilei is? What is Galileo Galilei known for? So this is actually quite a common misconception. So Galileo Galilei didn't invent the telescope, but he was the first person to use the telescope to discover other planetary bodies that is too faint to see with the naked eye. And that is something we will discuss in next week's lecture. So I think let's call it for today. Thank you for participating in my class. Thank you for attending it. Thank you for the class participation. It really means a lot. I will remain active for another minute or two if you would like, if you want to ask any questions. Otherwise, have a wonderful week. Good luck with the rest of your week. And I will see you all in next week's class. I'll keep you informed if the class will be online or in person. So is there a WhatsApp group for this class? So many people shared a link. So there's not a WhatsApp group. I created a Discord server for this page, for this class. It's a pleasure, guys. I will quickly paste the Discord link again. Let me quickly copy. I will provide it on ClickUp as well. But here is the link again. It's a pleasure. If there's no further questions, then I'm also going to log off. Have a wonderful evening. Good luck with the rest of the week, and I will see you all next week.